Hello, my dear students. Today, in this lecture, let us see what is psychrometry and the psychrometric properties and what is psychrometric chart. Me, Dr. Shrikala from the Department of Mechanical Engineering, Global Academy of Technology. Now, let's see what is psychrometry. Psychrometry is a science that deals with the physical laws of air and the water vapor mixture. That means we study here the atmospheric air and the thermodynamic properties and its thermodynamic properties to analyze the different processes involved in it. This is obtained from the Greek word sukron, which means cold, and metron means way of measurement. This is mainly used in designing air conditioning systems, HVACs, many heating and cooling processes. Next, see what is air conditioning. Air conditioning is defined as a process of conditioning and maintaining the controlled atmosphere. That means depending on the weather conditions existing and the required condition, we undergo it. Some of the processes are undergone, and that process is known as air conditioning for comfort. Normally, to understand is important before getting into air conditioning or conditioning the air. So we need to know what are the properties of the existing air and then get into the conditioning processes. Normally, any air or the atmospheric air consists of mixture of dry air and the water vapor. Water vapor content normally varies between 0 to 3%, and the dry air is composed of many gases, mainly the nitrogen, which is of 78%, and oxygen 21%. The remaining 1% includes all other gases as inert gases such as hydrogen, helium, argon, and also carbon dioxide. Now let's see what is psychrometric chart. It is nothing but a graph of thermodynamic properties of moist air at constant pressure. We'll get it in detail in further lectures. In this lecture, let's see what are the main important 5 properties which are used to describe the characteristics of the air. So for mainly 5 properties are used. Example that they are dry bulb temperature, wet bulb temperature, dew point temperature, relative humidity, and humidity ratio. Now let's see what are these temperatures. First one, we'll see dry bulb temperature. Dry bulb temperature is nothing but the ambient air temperature which is used to measure, or it is measured by the standard thermometer, and that is specified by dBT. Next is wet bulb temperature. When the thermometer is covered by a wet cloth, and when this thermometer is exposed to the current of air, then the moisture present in the wet wick evaporates and cools the bulb inside. Hence, that temperature is known as wet bulb temperature, and this temperature will always be less than the dry pump temperature, that is dBT. Next is wet bulb depression. The difference between the wet bulb temperature and the dry bulb temperature is known as wet bulb depression. Normally, when the air is saturated, that means when the moisture content in the air is maximum, then this wet bulb temperature will be equal to the dry bulb temperature, and the depression will be, or the difference will be 0. This, when the air is dry, then the wet bulb depression will be very high. That means difference between the dry bulb and the wet bulb temperature will be high. Next, let us see what is dew point temperature. This is the temperature at which the moisture present in the air begins to condense when air is cooled. When the moisture begins to condense, when the air contains the moisture at its extreme level, that is the maximum amount of moisture which the air can hold. When the limit is reached and when the further air is cooled, then the moisture in it starts getting condensed. Example, let us see. Early morning, if we see, we can see small dew drops over the grass. This is because generally during afternoon times, temperature will be very high and the capability of the air to contain the water vapor will be high. As the temperature goes down during night times, the capability of holding the moisture starts reducing. But by the time in the early morning, when the temperature is so low that the atmospheric air will be so cold, that means it will be unable to hold the water vapor in it and starts releasing the latent heat, and the water vapor in it starts condensing. That's why early morning when the temperature is low, we can see the dew drops. Especially this occurs in the moist region when the temperature or the atmospheric air is humid. So this dew point temperature is nothing but the temperature at which the moisture present in the air begins to condense. That means when the air is saturated with the water vapor, it begins to condense. That temperature is known as dew point temperature. So when all these temperatures will be equal, when the temperature of the air or the dry bulb, wet bulb and dew point temperature, these temperatures become equal or become same when the air is saturated. That means the air is in such a condition that it can hold no more of moisture, or when air is completely saturated with water, then these three temperatures become equal. Next, let's see certain ratios. First one is the humidity ratio or the specific humidity or humidity. You can be called anyway, and that symbol is omega. It is nothing but the ratio of the mass of the water vapor to the mass of the dry air. Example, consider some amount of moist air. In the moist air, separate out the water vapor in it and the dry part. So if we weigh these two, the ratio of mass of the water vapor to the mass of the dry air is known as omega or the specific humidity. Next is relative humidity. This relative humidity is defined as the ratio of partial pressure of water vapor in a given volume of the mixture to the partial pressure of the water vapor when the same volume of the mixture is saturated at the same temperature. That means if we consider some amount of moist air and measure the partial pressure of the water vapor in it, that will be the numerator, and the same moist air when it is saturated, and then if we measure the partial pressure in it, that is known as that PVS or the partial pressure of the water vapor when the air is saturated. The ratio of these two is known as relative humidity. The other important properties are Dalton's law of partial pressures. What we have already studied, Dalton's law of partial pressure means in a total pressure of a mixture of gases, Dalton's law says that the total pressure will be equal to sum of the partial pressures which are exerted by each gas when all these gases occupy the same volume mixture and when they are at the same temperature. So for total pressure will be equal to sum of the partial pressure of the dry air plus partial pressure of the water vapor in a moist air. Next is degree of saturation. This is nothing but the ratio of actual specific humidity to specific humidity of the saturated air when water vapor is at the same dry bulb temperature. and the pressure. That means it is nothing but the ratio of the specific humidity of the moist air to the specific humidity of the moist air when it is saturated. What do you mean by specific humidity? It is nothing but the ratio of the water vapor to the dry air, mass of the water vapor to the dry air. That means we'll see here. Yeah, we'll get into that in detail in the next slide. Here we'll see the definition of saturated and unsaturated air. Saturated here means at a given temperature and pressure, when we say air is saturated, when the amount of water vapor has reached its maximum limit, then that is known as air is saturated. And when air is saturated, the relative humidity will be 100%. On the other hand, when the amount of water vapor is in the air is less than this maximum limit, so in the normal moist air, we call the air is unsaturated. Next is adiabatic saturation temperature. That means the temperature of the air measured when the air is saturated. How to make the air saturated? This can be done by passing the air through an adiabatic conduit where we have some amount of water is present. As the air flows over the water, this absorbs the moisture, and by the time it comes out of the conduit, the air will be completely saturated, and the temperature measured at this condition is known as adiabatic saturation temperature. Let's see some of the important psychrometric relations we used here. One is the specific humidity ratio, as we have already seen. Now we'll obtain some expressions using this. Consider amount of moist air. Let the air has MA kg of dry air and MV kg of water vapor. That means water vapor mass is MV and the mass of the dry air be MA in some amount of moist air which is taken in a vessel of volume V, which is kept at the pressure P and temperature T. Now, by definition, specific humidity means it is nothing but the ratio of mass of the water vapor to mass of the dry air in a certain amount of moist air. Now, let us assume the perfect gas equation. Assume that it obeys ideal gas equation. It can be written as separately for the dry air and vapor, water vapor. So PAV is equal to MARAT. That means partial pressure of the dry air into volume, since it occupies the same volume of the vessel, will be equal to mass of the dry air into the gas constant of the dry air multiplied by T. That will be one expression. And again for the water vapor, it will be PVV is equal to MVRVT. PV is nothing but the partial pressure of the vapor. Again, that vapor occupies the complete volume and it will be at the same temperature T. And that so, and MV be the mass of the vapor and RV be the vapor. Okay. So now, see here, this constant RA we know for the air is 0.287 kilojoules per kg Kelvin. And similarly, the gas constant RV is obtained by the ratio of universal gas constant R bar divided by molecular weight of water, because vapor means it is nothing but it is having water content. So how do you find the molecular weight of the H2O? It will be H. Molecular weight of H is 2 multiply. So it is 2 molecules are there. So 2 multiplied by 1 plus the oxygen. So what is oxygen molecular weight? It is single oxygen. So it is 16. If it is O2, it will be 32. So here one molecule is there. So it is 16. So if we get substitute here, we'll get RV as 0.461 kilojoules per kg Kelvin. This is the gas constant of the vapor and RA is the gas constant of the dry air. And dry air we generally know it is 0.287. Next, From that we obtain MA. So PV is equal to MRT. So what will be mass of the air will be equal to PAV by RAT, and mass of the vapor will be equal to PVV by RVT. Now substitute these two expressions in the specific humidity. So specific humidity will be equal to mass of the vapor divided by mass of the air. So mass of the vapor is PVV by RVT divided by mass of the air is PAV by RAT. So substitute here, V and T gets cancelled. We'll get PV into this RA goes onto the numerator, PV into RA divided by PA into RV. So that will be equal to PV into what is RA? Gas constant of RA is 0.287 divided by PA into what is RV, which just now we obtained the expression as 0.461. That will be equal to, this ratio is 0.622 PV by PA. So what is PA? We know PA is nothing but what? Total pressure will be equal to partial pressure of the air plus partial pressure of the vapor. So what is partial pressure of the air will be equal to total pressure minus partial pressure of the vapor. So PA is substituted as P minus PV. So from this we say, since the total pressure P remains constant, so the specific humidity is just the function of partial pressure of vapor only. Hence, vapor is assumed to be behaved as perfect gas and the assumption is valid. This is the expression for the specific humidity, and this you have to remember to solve the numericals on psychrometry. Next, let us see degree of saturation. What is degree of saturation? Actual specific humidity divided by saturated specific humidity. What do you mean by actual specific humidity? That means if we consider some amount of moist air, then the ratio of, in the moist air, ratio of mass of the vapor by mass of the volume in that moist air divided by when the air is saturated, that time you measure what is the mass of the water vapor divided by mass of the dry air. This complete ratio is known as degree of saturation. Right? So we can write actual specific to omega, just now we obtained 0.632 PV by P minus PV. Similarly, when omega, that is when the specific humidity that is saturated, when the air is saturated, specific humidity omega S will be equal to 0.622 PVS, that means partial pressure of the water vapor when it is saturated, divided by P minus PVS. Now, substitute here. Mu is nothing but omega divided by omega S. So, omega substitute here, 0.622 gets cancelled. You'll get PV by PVS into, this numerator goes on to the top, P minus PVS. This numerator, in the numerator, P minus PV comes to the denominator, P minus PV. What is PV by PVS? We have just now saw it is nothing but the relative humidity. So, that will be equal to 5 into 1 minus, I am taking out P outside. So P, if you take outside, it gets 1 minus PVS by P divided by again P outside 1 minus PV by P. So this PP gets cancelled there, and you will get this expression. Further, we'll continue with the simplification. We'll get 5 into 1 minus PVS by P divided by, so in the denominator multiply and divide by PVS in this section. So we'll get 1 minus PV by PVS into PVS by P. So 5 into 1 minus PVS by P divided by, what is PV by PVS? It is nothing but the, again, relative humidity, just now we saw here. So 5 into PVS by P. So that will be, take this 5 inside, that is relative humidity, you will get 5 into 5 PVS by P divided by 1, it just remains same, 1 minus 5 into PVS by P. Now cross multiply. So omega into 1 minus 5 into PVS by P, that will be equal to 5 minus 5 into PVS by P. So take this mu inside. So mu minus mu 5 into PVS by P, that will be equal to 5 minus 5 into PVS by P. That will be equal to, so now simplify, you will get mu will be equal to 5 into 1 minus of 1 minus mu into PVS by P. Or 5 will be equal to mu divided by 1 minus mu into PVS by P. This is the expression which says the relationship between the relative humidity and the degree of saturation. The next we'll obtain one more expression on the enthalpy of moist air. So what is enthalpy? Enthalpy is nothing but the amount of heat contained or the energy, heat energy in the moist air. So that will be equal, since moist air means it is nothing but the combination of dry air and moist air. So we'll say enthalpy is nothing but the combination of enthalpy of dry air and enthalpy of moist air. So M into H will be equal to MAHA plus MVHV. So small h is nothing but specific enthalpy, that means per kg, that's why multiply by, so total M, total mass of the moist air will be equal to mass of the dry air and into enthalpy of the dry air plus mass of the vapor into enthalpy of the vapor. Now, so what will M into H? So what will be H will be equal to MAHA plus MVHV by M. This is per unit mass of the moist air. If we consider per unit of dry air, we will divided by HA. Sorry, divided by MA. That will be equal to H is equal to, so MA gets cancelled, you will get HA plus MV by MA, this into HV. So what is HA? Keep it as it is. What is MV by MA? It is nothing but the ratio of mass of the vapor to mass of the dry air is nothing but the specific humidity, omega into HV. Now, what is this H? H is nothing but, what about HA? HA is nothing but Cp into dry bulb temperature plus omega into HV as it is. Now what is Cp of the air is nothing but 1.005 kilojoules per kg Kelvin. Substitute here. Now H is equal to 1.005 into Tb plus omega into, what is H of the vapor? Vapor will be equal to, we have already studied in BTED. So as superheated vapor, if we say, it will be Hg plus Cp into delta T. Tdp minus Tdp. Dry bulb temperature minus dew point temperature. That means it is the point where the temperature, when it is saturated, where air is saturated. Substitute. Finally, we will get the expression as H is equal to 1.005 TdB plus, TdB is temperature of the dry bulb temperature, plus omega into 2500 plus 1.88 TdB. We need to remember this expression in order to solve the numericals. These are the certain expressions which we use for solving numericals. Next, we'll see what is psychrometric chart. Normally, the atmospheric air can be specified at any specified pressure, can be completely described using only two independent properties. Independent means which is independent of the mass, we say, that is intensive properties. Those two are dry bulb temperature and specific humidity. So the psychrometric chart is a graphical representation of these process, wherein if the x-axis is on the dry bulb temperature, on the y-axis we have specific humidity. So using this psychrometric chart, we can obtain certain thermodynamic properties and try to find out the conditions of the air, and also many of the properties can be obtained using this chart. Now, so this chart, psychrometric chart, as I see, let us see individually about the psychrometric chart. This horizontal x-axis is, as I said, is the dry bulb temperature. So these vertical lines which we see shows the dry bulb temperature lines. These horizontal small lines are the specific humidity lines. Here, lines which are at an angle, which are highlighted, are the wet bulb temperature lines. This line, pink line on the topmost position, where it is the saturated line, or when the relative humidity is 100%. So as you go down, the relative humidity goes on reducing. So at x-axis means it is completely, air is completely dry and humidity is 0. So these extended lines you can see are nothing but the values of enthalpies in kilojoules per kg of the dry air. So using these lines or using this chart, we can solve the problems regarding psychrometry, wherein the required condition and the exist using the exist condition, and what are the processes required to obtain the required condition, that is air conditioning, can be used solved numerically using this psychrometric chart. So this different processes which are required to obtain the comfort condition will be dealt in my next lecture on psychrometry, or the in that psychrometric properties. Thank you.